Okay, today's lecture is quite interesting. I would say that I'm quite excited about it because before I got into coding, I still am a mathematician, and I specialized in graph theory at uni. And this is a very interesting subject, and it's relatively simple compared to other math, courses and disciplines and so on, but at the same time it's very rewarding. It has many applications, like real world applications that you actually use probably every day, so like the GPS on your phone, Google Maps and so on, databases on the internet, and many things use graphs. They're efficient, quick, and not so complicated to understand and to look at. So this is a lecture about that. All right. So what are we going to be doing today? We have what are graphs? Are they useful? Well, yeah, clearly, if we are doing them. Okay, then we'll implement our own generic graph. We'll do. I wouldn't say in much depth. I wouldn't say in much detail the depth first search. And after that, using the depth first search, we will hack the Wordz game. So how many of you have played Wordz game or Oldumi, or at least have seen it? Okay, so we'll hack that. We'll have all of the words that we want, and we can cheat the game this way. Okay, and I've given optional exercises if you're interested in the topic. I have kept them relatively simple. The idea is to go through the code and extend it a little bit, add a type of graph, add one more algorithm and stuff like that. So just to see if you understand, if you can get your way around the code. All right, what are graphs? Okay, a graph is roughly said a collection of vertices or points and edges or lines between them. So from now on, every time when I say a vertex, imagine a point, and every time when I say an edge, imagine a line between some of the points. All right, edges can be directed, and then our graph is called directed. They can be undirected, colored, weighted, and so on. Anyone else have any other, examples of edges? I think there are some more. I mean, there are very many different types of graphs, and I'm sure that I'm missing something here, but just to get the idea. So if I go back a couple of slides, this is the Peterson graph, and it's quite interesting, but I wouldn't go into much detail why. So yeah, here we have some points. Let me launch zoom it, and yeah, because there's going to be a lot of drawing today. Right, so please, yeah. All right, so this is a point or a vertex, and here we have lines between the vertices, and this whole thing here is called a graph. No, just a line there. Okay, is that clear? Nothing complicated, right? So, are they useful? Well, yes, and they have some really interesting applications, as I mentioned. So pathfinding GPS systems use that. If you imagine that each point is an intersection, and here we have some streets around it, and maybe some more intersections and so on. This is still a graph, right? And to calculate the shortest path from one point to the other, so let me make it a little bit bigger. So let's say that I want to go from here to here, start and finish. And here I have some arrows, some ways, there, maybe there, and this is both ways. You can do that. All right, so the idea here is that each of these edges can have some number, so they're weighted. So I can have something like a 2 here, and 3 here, and 4 here, and 5 here, and so on. Right, so now it's, well, this example is very, very simple, where I only have one path, right? I can just go from this point. Let me change the color. I can go to this point, and then I can go to the finish in only one way, and this is gonna cost me 5. This 5 can be, kilometers, meters, any kind of weight that you want. So yeah, GPS. So yeah, this is a simple example, and imagine if you have a really huge network where you can actually get I don't know, thousands of paths, and you have to calculate which is the shortest. Then it's not going to be that clear what your solution is, right? And there are algorithms that do that for you, and they use graphs, at least in the theory. They use graphs to do that. Okay, then we have matchings, we have different algorithms, NoSQL databases, and many more. So I have some slides here with some pictures that can probably explain it a little bit better. So yeah, this is the example that I gave. So let's say that we want to go from P to U in the shortest possible path. Can you find it? P, Q, R, U, right? Because I have 1, 1, 1, that's 3 in total, but I have many more, right? So I can go PSU, I can go PTU, I can go PSTU, and so on. So there is an algorithm, and I believe that I've given it in the exercises. It's not that complicated, and I'm sure that you will be able to do it. So once we implement the whole graph system in this lecture, you'll be able to use all of the structures that we have, and just implement an algorithm that's a couple of lines of code, and then you'll have this algorithm. You can try and apply it for a larger system to see if it works, and so on. So yeah. Alright, so these are matchings. So what's a matching? Imagine that you were applying to the UK through UCAS. How many of you know what UCAS is? Alright, so UCAS is a website where you can go and you can apply to universities. Okay, and imagine that on the left side we have students. So let me draw that. So students. And here we have universities. Okay, so let me put some labels here. So A, B, C, D, E, and here we have 1, 2, 3, 4. Okay, so after all of the applications have finished, you can get something like this, which is going to tell you which student has applied to which university. So we have this first guy A. He's only applied to University 1. Then B has applied to 1 and 2. C has applied to 3 and 4. D has applied to 2 only. And this guy E has applied to 1 and 4. Right? It's very clear. So what kind of algorithm would you expect to be useful here? So what can I do with this information? Why would I need to model this with graphs? What kind of information, or what would you like to do with this information? Any ideas? Once you have it, because it's fine just having the points, and they point to the uni, but of course you can do that on the website. You can just check who's applied to what. So this is just for information purposes, but we would like to be able to do something with this algorithm, with this graph. Sorry. Any ideas? Check how many people have applied to one university. Well, yeah, you can do that, but it's not that much of an algorithm, right? You just check. Okay, so the idea here is that there could be a certain way where as many students as possible have gained a place at university. Okay, so say that 10,000 have applied. If you do a random matching, only 5,000 of them will get a place at a uni, and maybe you would like to have all of them or as many as possible to get in a university, right? That makes sense. Yeah. Okay. So this is these are called matchings, and they're used. So the algorithm, I don't quite remember the name, but it was used in the States from a very early stage and like a while back to match doctors to hospitals. After they have to do their placements. And in the UCAS system, I think it's used since 2007, so a bit newer. Yeah, right. So these graphs are called bipartite, and if you can see the set of students here, the vertices which map the students, they don't have a connection between themselves, right? And this is the same for the universities as well. I don't have any edges here on this side of the graph, so these graphs are called bipartite. Okay. Not much more that I will say. If you're interested, you can go and have a look. You can have a look at the algorithm as well. You can implement it if you want for homework, if you'd like. Yeah, so just if you're interested, you can go and have a look. All right, so this is what I think is called a folder tree, and I'm sure that all of you have seen something like this, where you actually search on your how's that called? Explorer, yeah. Yeah, and you have all of the folders listed, and if you click on the plus sign, many more come up and so on. So this is also a tree, which is a special type of graph, where this is my vertex, and here I have my edges. You know, they're more visible. Here I have more vertices. Right, and here I have some more, and so on. Right, and what we are going to be doing today is depth first search, which can be used when you search through your folders, like for some file or something like that. It's I'm not sure if this is the precise algorithm that it uses. Maybe it has some optimizations and so on, but this is one way that you can search through your folders if you want to get a specific file or something like that. What else are they useful? Does that look familiar? Chrome, okay. But does anyone know where the logo actually comes from? This is a more complicated question. Alright, so there is a theorem in graph theory which is called the four-color theorem, and it says that every single 2D map, well, this is roughly said. I don't want to go into specific about the theorem, but any 2D map, like imagine map of the world, can be colored with 4 colors. So that no neighboring regions will have the same color. All right, and you wouldn't need any more. So independently of how complicated the map is, you are only gonna need four colors to find a proper coloring of the map. And yeah, so this is an example of that. So we first see this one. It's pretty clear. You only need four colors. This one gets a bit more complicated, but you can still do it. This one is a bit more complicated. Now these two are actually the same, I think, but this one is now a bit more complicated, and you can still do it. It doesn't matter how complicated the map is. You can always color it with 4 colors and no more. Well, you can use more, but that's not the point, right? So they've come up with this number 4, and they said, well, that's all you need to color a map. What's interesting about this theorem, that it's the first theorem proven by a computer. Has anyone heard about this? No? So the story is actually quite interesting. I don't want to go into detail. You can read it online. So this is the four color theorem. If you want to check that online. Yeah, right. So graphs are useful, is my point. Alright, we would like to implement our own generic graph and see how we can use it. Is it good? And as an application, I would like to hack the Wordz game. We'll be doing depth first search as well. I'll leave that as a homework since it's a little bit easier, I would say. And yeah, so while we do the demo, since there will be many new things for you at this stage, I would just like you to keep in mind that this is like a practice on the following. So we have generic classes. You have to write your own generic list, but I believe that it's a lot simpler than what we are going to be doing today. So this is a more like real life example when you actually need to create something on your own and use it for some algorithm. Or something else. Alright, you have to keep in mind the quality of the code. I've tried my best to write this as well as possible. Inheritance, subtraction, encapsulation, cohesion, coupling, and of course some algorithms in there that we'll add, which we haven't done so far. Actually, I think you had some recursion algorithms in your first course, but they were all optional, so I don't know if everyone has done it. Alright, so let's get into coding, because that much theory is for mathematicians. And Visual Studio, please. Perfect. Now I have to find it. Does anyone know where that is? Or I can just yeah, I can just open up a project and go from there. So yeah, Microsoft, please fix when you release in a month and a half. Please fix this. Yeah, has anyone else gotten this? Nope. Ever?
Yes.
Yeah. Okay. So the start button, you know, bugs. Right. Alright, so let me close this up now, and so can I unload or close or something? No, let me just make a new one. So this is gonna be called graph theory examples, or generic graph. Yeah, that's fine. Alright, let's rename this. So this is gonna be something like testing or entry point. Let's call it entry point. Okay, so in about an hour and a half, in this in here we'll be, you know, testing our graph. So let me remove this. Get all of the usings inside. Actually, I have to delete most of them, and then we'll add them as we go along. Make this class public, make the static void public as well. Alright, let's have a look. So the first thing that I want to do is create a folder which is going to be called model, and inside here I would like to start, you know, making my graph. Okay, so what does a graph need first? So the first thing that comes into mind, vertices. So let's do that. Let's add a new class, and that's going to be called Vertex. Right, and okay, press enter. Right. So let's remove that. It's going to be in the namespace module, and it's going to be public, although it doesn't need to be. But I'll explain that as we go along. All right. So the vertex can have a label, right? So if you remember, I labeled the students in the universities with different symbols. So the left hand side, so the students were with letters, and the right hand side were with numbers. So we have to have some information about the vertex. What does it hold? So in one case it was holding students, right? And in the other one it was holding universities. So I can hold both numbers, letters, classes, and so on. So we have to make it a generic class. So this is going to be vertex of t. Is that clear? So yeah, if you have any questions, just stop me. I'll be just going along a little bit faster. All right. So the first thing that we will need is private list int of weights. Weights. Right? Why do we need that? Sorry. Collections generic. Yeah, I'll add that. Thanks. I'll be fine with that. Thanks. Right. So I can add that. Control dot insert the using, put it inside the namespace. Right. Okay. So list of ints, which is going to be weight. So we would like to hold the information of all of the neighbors of my vertex. So we'll have a list of vertices, and each of them is going to have a weight on it. All right. So after that, I would like to have private t data. So the data, is it like a specific student? Is it like I don't know, a number or of some sort? And this is going to be my data inside the vertex. All right. And after that, I would like to have private vertex list of t, and there's going to be neighbors. So every vertex has a list of neighbors, and each neighbor has some weight on it. We don't have this. I'll just add it so that Visual Studio is not mad with us. New class, and I'll call it vertex list, and this is going to be, I think it was of t as well. Make it public. Delete all of that, and I'll leave it as is, and we'll fill that in as we go. All right. So once I have, so this thing pretty much is gonna hold all of the. It's gonna hold some vertices. So the only thing special here is that I'll have a list of vertices, and then maybe I can access them through an index or something like that. We'll see, but it's not that complicated, this one. All right. So what do we need? Well, we need constructors. So let's add the empty one. After that, we have a constructor which is going to be with a value. So I would like to say t value, and here I would like to say just leave it as is, I think, and maybe we want to instantiate a vertex with a value as well as a list of neighbors. So vertex list of t, and we are going to call this neighbors. All right. So here, what is it that I want to do? Let me first add the properties here. So I have prop, which is going to be just one second. So t value. I said value. So this is what we are going to give to the outside world. Okay. So if someone wants to access the vertex and get the value, this is how we are going to present it to the outside world. All right. So I would like to extend this. Not this way though. Anyways, it'll be fine. All right. So here I would like to have what do you say that I have? Return data. So Why do you think I did not call this value here and data, right? Because you know this is going to be value, right? I could have just said value here. Any ideas? No? Really? It's a reserved word. Well, I can use it here, but once I get to the set, I would like to say I would have to say this dot value equals value, and those are gonna mean two different things, right? This is why I decided to rename it as data, because I believe it's gonna be confusing otherwise. So here I have to say return this dot data. That's gonna be fine, and then I wanna do a set. Which is going to be this dot data equals value. All right, maybe some type checking is due. I don't know. I'll leave it as is. So if am I missing something? Yeah, another bracket. Yeah, please work. Okay, we are fine. Okay, after that I would like to do the same thing with the vertices. So public vertex list of t. And I am gonna call this neighbors. Okay, so maybe I would need to access, and actually I will access the neighbors for each vertex. Is it clear what a neighbor is? So if I didn't explain this. I thought it was kind of obvious. So let's say that I have this vertex here 1. So it has 3 neighbors. Okay, these 3. All right, and each of them is a vertex on its own, right? And if I say, well, this vertex, let's say that that's called A, I would like to be able to say A dot neighbors like this, and it will just give me the list of all of its neighbors, which is going to be of type vertex list. Right here, right? The neighbors, since they are a collection of vertices, they will be of type vertex list. I'm sorry that I did not explain that earlier. All right, so get, and here I would like to say return this dot neighbors, and in the set I would like to say return this dot neighbors equals value. Okay, and I have to do the same thing for the weights as well. So public vertex list. What was that? List of int vertex. Actually, they shouldn't be integers, because normally weights can be decimal numbers and so on. I can change that, but let's leave it as is, because to be honest, we won't be using the weights. They will be for your homework if you decide to do it, but let's just put it in there so that it's available. Alright, so public list int, we are going to call that weights, and I would like to have a get which is going to say return. Actually here, the way we are going to use the graphs is you may be able to instantiate a graph without weights. So I would like to make sure that if you do this, you are not going to get an exception. So I would like to say if this dot weights equals no, meaning if I haven't given weights to my graph, then I want to say this dot weights equals new list of weights, list of int, this way, and only after that I would like to say return this dot weights. Alright, the weights are not gonna have a set, so once you've given it, then it just remains as is. You cannot change the weights. If you need to, you can always come back here and implement a set operator, but yeah. All right, so let's get back to our constructors once we have this. So I would like to say in the most in the third one, I would like to say this dot data equals value, and now this value comes from here, and after that I would like to say this dot neighbors equals neighbors. Okay, any error here that you see? I should access it through the property. So this is a mistake in my code as well. Let me fix it, and yeah, I'll be sure to fix it after. Okay, so now let's reuse some code. It's gonna be yeah, this is value. Thanks. All right, so let's reuse some of the code that we've just written. So there's gonna be this, and I would like to say value, and inside the list of neighbors, I would like to say just new vertex list of t, and that'll be it. So if I don't give the vertex list, just say that it has an empty one and create it, right? Is that clear? What this thing does? Let me put it this way. So yeah, when I was writing this, I had you know some exceptions going on, and it was exactly because I didn't instantiate an empty list of neighbors here. And here, what we would like to do, actually, this one remains as is. Okay. Okay. Is everything clear? This is, you know, pretty simple, except for the fact that we have, you know, the vertex t, which is a generic one. But other than that, it's like a normal class. So we have weights, we have some data, and we have some neighbors. The constructors are clear, and then we have properties to access all of the information that we need. All right, so let's fill in the vertex list. This one will be slightly more complicated, but not much. All right, so I would like to add some usings here. So using system is what we use, and one that you probably haven't had the pleasure of using is system dot collections dot object model, and we'll see why. Okay, so first of all, I would like my vertex list to be a collection of vertex of t, and I would like to implement iClonable, the iClonable interface. All right, so yeah, I haven't implemented it, but yeah. So let's see what's in a collection. All right, so this is a vertex list. We'll be using that for the neighbors of each vertex. So it's exactly what it says. It's a collection of vertices. So let's see what this class gives us. All right, so we have an indexer already. We have count. We have the items. Okay, we have add. We have clear the list. We have add a list. Add an item to the list. So we don't have to implement any of that, right? It's pretty cool. Then we have contains, copy to. We have enumerator, so we would be able to iterate through the collection with for each. We have index of, which is cool, insert, remove at, and so on. So all of these cool things I get only by saying in here that I would like to inherit from collection of vertex of t. Okay, the iClonable is just an addition. We'll need it for one of the algorithms. This pretty much says if I want to clone, means that I want to make a proper copy of my vertex list and not just copy the reference, right? I want to make a completely new one, which is a copy of the previous one, and not just copy the reference. So let's see what this gives us. So this is just a method clone that we have to implement. I'll delete it for now, and we are going to implement it in a second because it's a bit tricky, this one. And let's start doing our class. All right, so public actually constructor. I would like to say vertex list, and this is gonna inherit from base. Right? I have this thing, and I can just inherit from it, and why not? Right. After that, we have another one. So constructor, have public. Sorry. Inside here, I would like to say int initial size. Okay, and inside here, I would like to add some values to my vertex list, which are like an initial size. Okay, so if I want to say I would like to have a vertex with 5 neighbors, this is what this is gonna allow me to do, right? And there will be default ones if you wanna use that. So from 0 to initial size I++, and after that I want to say base.items.add default vertex of t. Alright, so this line I didn't come up with it myself. I had to look it up what it does. So the idea is that I'm actually accessing the items which I already have from my collection, and I want to add and this default here you probably haven't seen. I want to add a default value of a vertex of t, which in this case is just going to be an empty vertex, right? So this thing just creates some neighbors, if you want to think about with a specific number. Right. After that, what is it that we need? Public object select get internal set. I have no idea what this thing does, to be honest. I'll be completely honest. So select, what would that do? I have no idea why I have this. Let me put a comment here, and if we don't need it, I'll delete it after that. All right, now comes the cloning bit. So public vertex list of t is going to be clone. All right, so when we clone, we actually want to return a vertex list, right? So this is the idea. All right, and here I want to say this is pretty standard. So vertex list of t, new list. This is the list that I'll be returning. Equals new vertex list of t this way, and for I from 0 to this dot count. So if I wanna clone a vertex list, which I already have, which is going to be the one that I've instantiated, and I want to say clone, I want to copy the one that I have. So this dot count. So I want to copy the one that I have currently. So this is why we have this here, and I simply want to say new list dot add, and I want to say this of I. Okay, and I'm allowed to say this because we are doing the collection, and as we saw, it already has an indexer right here, right? Otherwise I wouldn't be able to do it, and I have to do everything from scratch. But we have a lot of things that come straight from the parent class. All right, and the final thing is just to say return new list. Is it clear what we do here? I just copy it value by value. Instead of, so I create a new one. So this is gonna set a new place for it in the memory. So I create a completely new list. I copy each value, and after that I just give the list back. Otherwise, if I want to say list 1 equals list 2, I will only copy the reference. If I want to create a new list, which is a real copy of the one that I have, then we have to do it this way. Otherwise, it's going to be copied by reference. Is that clear? Do you have any need here for some more? Okay. if you can see, I still have not implemented the iClonable because it actually requires an object to do so. So let's do that as well. So it's going to be somewhere down here. And so I've already done the method, but to implement the iClonable interface, I would have to return an object as well. So here, the only thing that I have to do is return this dot clone, which is going to be the method above. So this is a bit tricky. So every time when you have to implement the iClonable interface, first you do it the proper way, you know, with the return type to be expected in this case is going to be vertex list, and after that with the object we just copy the clone method in here. Is that sort of fine? Okay. What else do we have? Okay, I would like to be able to find a vertex by value, so let me put that here as well. So public vertex of t, find by value, and this is something that we'll be using quite a lot, t value. So right now I actually have a method which is, you know, like index of, but it is gonna work only for a vertex, and I would actually like to be able to find it by value, not by the specific vertex. So let's say that I've created a vertex. So add graph dot add, and inside here I would have to say vertex 1, where vertex 1 equals new vertex, and so on, of say value 5. Okay, I would like to implement a method where I can just say 5 here, right, and that'll be it. So yeah, this is why we do this. Okay, so let's have a look. All right, so for each, and I would like to say vertex in this dot items. So this dot items is what we get from the parent class, which holds all of our items. Like it's a collection, and the items are exactly the list of collections that we have. Actually, we can have a look at this. If you want to, you see it's I list of t, nothing special. It's just a list of the items, or in this case, the vertices that we have, and I can use it straight away because I inherit from the collection of vertex of t. All right. So what do I want to do here? If vertex dot value dot equals value. Okay, so here I take the vertex, I take its value, and then I want to say, well, if it equals this value that I have given, then this is the vertex that I want, right? And inside here I would just like to say return vertex, means that I have found it, and otherwise I would like to return otherwise I would like to return no, meaning I haven't found anything. I have to make it. No, I should put it just outside. Sorry, yeah, you are right. Just put it outside. So if we find a vertex by the value, then just put it back. And if we don't, then just we haven't found anything, and we just return no. Is that fine? Everything here that we've done. Let's have a look at it again. So now our vertex of t has some weights. Actually, let me put that a little bit down because it's not that important. Okay, so first of all, we have data, which is going to be the value of our vertex. So something like this is it. I can have a 1 here. I can have a letter like A. I can have a bunny if I want to, any class, anything that I want. If I wanted to specify, I could have done it here. Have I shown this where t is, and you list some I don't know, I enumerable and so on. you can do that if you want to. Just specify what you want t to be, but in this case we don't really care because it's just a value that we hold, and we don't need any specific properties for the value. It's just a label, right? Nothing special. All right, then we have the list of neighbors, which we just implemented. So let's get back to that. Okay, so this is just a collection of vertices, nothing special. We just added a constructor with a specified size. We added a clone method and just find by value. So nothing special. It's just a collection of vertices. Right. Okay. So we have some constructors here. We have the value. We have the neighbors, and we have the weight. Okay. So nothing complicated now, right? Everything is fine, I guess. I hope. Yeah. Any questions? Sorry. So far everything is fine. All right, let's get back to the actually let's start with the more complicated things then. So now we would actually like to make our graph, which is gonna have a lot more things. Now that we have the vertex and the vertex list, so now we are gonna implement the graph, which is gonna take care of the edges, like holding the vertices, iterating through them, and so on. So this is gonna be you know, the key class for today. So I'll just call it a graph. All right, and in here I would like to remove all of that, make this public. To be honest, everything about the graph, like vertices and what else, like neighbors and edges and so on, will be available through here. So in all honesty, if I was to export this library, I should have said here everywhere instead of public. I would like to say internal, right? Because if I want someone to use my library, then I wouldn't want him to be able to see what's in the vertex of t, but only to present him with the information that he's going to get from the graph, right? Internal here is going to allow me to access everything in this project, right? So that I can implement my graph, you know, access everything from the vertex if I needed to. But if someone was to be using it outside, they would need to see how I implemented my vertex, right? Is that clear? Yeah, I'll leave it as is now. Let's not get that much into the details, and let's start doing the graph. So this is going to be a graph of t as well, and it's gonna inherit from it's gonna extend I enumerable I think of vertex of t. Alright, so the graph here, I say that I would like to be able to for each the graph, and it's gonna give me the vertices. Is that clear? So I enumerable means for each, and since we don't have it as a given, we have to implement it a little bit later. Alright, so here I would like to say, so what using this this thing wants. Let me have a look. Control dot collections.generic, put it inside here. Is there anything else that I'll be using? Inside here it says using system. It says also using system.collections. Okay, and right, so let's have a look. What do we need? So the first thing that we need, so what does a graph have? It has a list of vertices, right? So I want to have private vertex list of t, and this is going to be vertex set. This is how we are going to call it, to be relatively clear. Alright, so let's make some constructors. We are going to have one which is empty. We are going to have another one which is going to take a vertex set, so vertex list of t, vertex, how did I call this? Vertex set, I guess the same name. It's not that good, but you know, no way around it now. Okay, and here I want to do something similar to what we did with the vertex. If I don't have a value, I would like to set it, as an empty list. So if I don't have any vertices, I would like to create just a new list. So this is what we'll do. If vertex set equals null. Actually, I want to say, then I want to say this dot vertex set equals new vertex list of t, and after that I would like to say else. So if it's not null, the thing that I am giving here as a value, else I would like to say this dot vertex set equals vertex set. All right, so if what I am giving is actually no, then I just want to create a new list, and if it's not, then I just want to set the value. So there will be, so this is another way to instantiate your graph. I can just give it a vertex set and it will be ready. But normally we're not going to be using it this way. We'll just be using it creating a new and then adding vertices one by one. So here I would like to say this of no, so that I make sure every time when I actually wanna create a graph that I'll have at least an empty list of vertices. Is that clear so far? Everything fine? All right. What do we have next? So we have public void add vertex. I'll leave it empty, and I would just like to list what we are going to be having. So add vertex. I would like to be able to add vertex of t vertex. I would also like to be doing public void add vertex just by value, so t value. And now I guess I'll go through them once I write them up. And okay, what else do we have? Okay, so we have here public void add directed edge, and we are gonna take vertex t from, and we are gonna take vertex vertex of t2, and I would like to have int weight. Okay, but maybe I wouldn't wanna add the weight. Maybe I just wanna create it empty, and to do that, instead of having two methods, add directed edge, one which has the weight as is now, and one without it, I would like to just say here equals 0, which is called a default value. Have you done this in the object-oriented programming course? This is new. Okay, so what this thing does is, okay, so if I give, if I actually say when I add an edge, I want to say from to. If I actually give a value weight here, it's going to be used inside, and I can use it. But if I decide to only give from and to and nothing else, we are just going to assume that the value is 0. This is called an optional parameter. No, I don't think so. Really? So the colleague here says that this thing only works in Visual Studio 2.15, and I would like to check that. So give me a second. Right, so this thing that I just did with the optional parameter works from Visual Studio 2.10 here. So yeah, it should be fine. All right. Okay, let's add some more methods. So I would like to do another one, which is going to be public void add directed edge. Instead of giving the vertex again, I would like to have t from t to, and of course again int weight equals 0. a default value if I actually don't want to give anything. So yeah, instead of, I just said that instead of giving a vertex, I can just give the value and find it from there, right? I don't want to over complicate things. So if I want to create a graph which has labels integers like vertex 1, 2, 3, 4, and so on. If I want to add an edge, I can just say add edge from 1 to 2, and that'll be a lot simpler than saying new vertex with value 1 and so on. So this is why I am doing this. All right, and of course we have directed. I would like to have public void add undirected edge, and it's going to be pretty much the same. So vertex t from vertex of t2, and I want to say int weight equals 0, and another one which I can just copy from here and call it add undirected edge, and it will be the same. Okay, what else do I want? These two. Sorry? I'll explain that in a second. Yeah, once I write them up. Okay, so this thing we don't need. This thing we don't need for now. What else do we have? Okay, we're up to the properties. So I want to have public bool contains t value. It's a simple method. I also want to have public bool contains vertex of t value, or sorry, vertex. Return false. Return false. We're gonna implement that a little bit later. Okay, what else? I want to have public bool remove vertex, and this is gonna be vertex of t vertex to remove. What else do I have? I want to remove by value as well. Remove vertex t value. Oh, come on. Return false. And okay, not much more, I think.
Why are your remove methods?
Sorry?
Why are your remove methods boolean?
Okay, if I found it, remove vertex. Why is it boolean? Let me. Okay, so if the vertex is present and I have removed it, then I am gonna give true. And if there wasn't such a vertex, instead of throwing the exceptions and so on, I'll just return false. That's why I have it. But if you just say graph dot remove vertex, nothing is gonna happen. It's just gonna remove the vertex. If you don't save the value of the boolean that I returned, then it's just gonna do its job. But if I want to check if I can remove the vertex, then do something, then I'll be using this. Then, yeah, okay. After that, so these come from the enumerator, and I have public int count, which is gonna be what happened. What did I press? Can I get back to English, please? Thank you. All right, so I'll just leave that for now. I would like to be able to access the vertices as well, so I'll have public vertex list of t vertices, and I'll implement that later. What else do we have? We have an indexer, so public vertex of t this int index, and I'll implement that a little bit later as well. Okay, the final thing is to just click here, implement interface, and we'll get two methods somewhere at the bottom. There they are. So we have to implement those two so that I can for each my graph, instead of just doing a for loop with the indexer, because for each looks better and it's easier to read. So if I can use it, then I shall. All right, so let's have a look. What do we have here? So we can add one. That's easy. We just add it to the vertex set. We can add it by value. We'll see what is different, and it's actually not that much. Okay, so directed edge means if I have a graph, if I have a graph, let's say 2 points. Okay, so how we're gonna implement this? So you can either have an edge which has an arrow, which is directed. It has a direction from one to the other, or I can add an edge which is this way, so just a line, which means that we can go both ways. Okay, so instead of creating two different types of edges and so on, I am gonna say, well, if I have a path from A to B, if I have a path like this and I have a path like this, well, this will be an undirected edge, and I'll be reusing a lot of the code, right? So let's say that I've implemented this. Here it says from, and here it says to. Then the only thing that I have to do in this method, add undirected edge, would be to say, well, add directed one from A to B, and then another one from B to A. So I'll be reusing the code very easily. And to us, honestly, so yeah, another thing which is cool here. So if I only have these two, A and B, what's gonna happen? So A is gonna have a neighbor, which is B, and B is not gonna have any neighbor, right? This is gonna be empty, right? If it's just from one to the other, right? But if I have an undirected and I've added both of them, then I will be able to have, A has a neighbor B and B has a neighbor A, and this is gonna happen just with a single method. And for the purpose of the demo later on, we will only be using undirected edges, which is what we need. So in order to implement one problem from your homework, you may need to add directed edges to test your problem. All right, so let's have a short break. After that, we'll implement this, and then the interesting parts are to come. Right, so let's get started with the implementation. So the first method would be very simple if we didn't have to do some checking. So the only thing that I have to say, this .vertex set .add, and I would like to say vertex, right? But it's not that easy, and the reason is that I am not allowed to add two vertices which have the same label, right? So I have to look through whether I have a repeating value or if I have the same vertex added already, and only then I can do that. So let's do this. So if vertex, what am I doing? No, this is not an if. Sorry. Okay, so for I from 0 to this dot vertex set dot count. Okay, I want to go through all of them and see if I have a matching vertex. So if this dot vertex set of I dot value equals vertex dot value. So I just check. So remember that when I say vertex set of I, it returns me a vertex, which is this class which has a lot of things and so on. If I want to access the value, I should explicitly say so. Otherwise, it's not gonna give it straight away. All right. So if they are equal, then I wanna throw new invalid operation exception, and inside here I wanna say you cannot add vertices with the same value. Now this is a good message. As soon as someone gets it, they will know what they've done wrong. All right. Okay, and just do that. Okay, so now this one is a little bit simpler because I can just reuse the code that I've just written. So I can just say this dot add vertex. So this is using the previous method, and I can just say new vertex of t, and I am going to give it value. So this is the constructor which creates me a new vertex by value. All right, that's fine. Okay, so now this one will be a bit more complicated, and in fact there is a to-do that I haven't implemented yet, but we won't meet this problem in our demo, so I just decided to leave it as is. Okay, so let's have a look. Just give me a second. All right, so if the point is here, I want to check if I already have an edge, then I wouldn't be able to add a second one. So I don't want to be able to, if I have a vertex here and here, if I have this edge, I don't want to be able to add it a second time, the same one. And this is the check that we'll be doing now. So if this dot vertex set dot contains from, or this dot vertex set contains 2 with an exclamation mark. So if I don't have this this vertex and or this one, then I want to do something here. I want to say throw new invalid operation exception, means you cannot add an edge from to non-existing. So I lied. The first check is if we don't have an edge. I'm sorry, if we don't have a vertex that we want to add from. So let's say that our graph has vertices which are 1 and 2, and I want to add an edge from 5 to 6. Right? That's not going to be allowed. Okay, and after that I want to say from dot neighbors dot add 2, and the second thing is from dot weights dot add weight. Yes. All right. So and the thing that I haven't done, so to do, if you want to, you can do it as a homework or just as an exercise. Check for repeated edges. Okay, which is not that simple of a check. I have to go through all of them, check all of their neighbors, and check if there is a repeated one, which is not that easy to. I mean, it's not that hard, but it would make this method a lot longer, and I just wanted to keep it as simple as possible. Okay, so what happens here? I want to say from, so the vertex from the neighbors, and I want to add a new neighbor, which is going to be the second one here too. Okay, and then I want to add the weights to my weight list of my vertex here. So this is my list of weights. All right, so let's get back to the graph and implement more. Okay, so now that we've done this, I can reuse it in all of the other methods. So I can say t from, and T2, which will be quite simple. So vertex T, how did I call it? V from equals this dot vertex set dot find by value from. So what I am saying here, if I want to reuse the code above, I would have to do it with vertex T from and vertex T2. I already have a method which we implemented, which is find by value. So only if I have the value from, which I am giving here, only then this yeah, as soon as I have this, then I can reuse the method above, and I have to do the same thing here. So vertex T v2 equals this dot vertex set dot find by value, and I have to say 2. Alright, and now I simply have to call this other method with these two. So let's do that. So add this dot add directed edge, and I want to say v from and v2, and that's it. And the good thing about this is that I am reusing this check, and imagine that I've done the check up here as well. I wouldn't have to write it twice, right? I wouldn't have to just copy paste it. If this thing here, sorry, if I don't have a vertex, then throw an exception and so on, I wouldn't have to rewrite it here. So I'm reusing the code that I've already written. All right, so we're up to the undirected edges. So as we said, this is simply if I have two points from and to, A and B, I will reuse the above methods, and I'll say, well, add an edge here and add an edge here, from A to B, and then from B to A, and this way I'll be still reusing the code from above. So let's do that. My first one is with the vertices. So yeah, I can simply say this dot add directed edge, and I can say from to, and after that this dot add directed edge to from, and that's it, right? I'm again reusing the code. Okay, if I only have the values, I have to do something similar from here. So I'll just copy that, so as soon as you have to copy paste something, that means that you're probably doing something wrong. But right now can I just reuse this? Can I just say add directed edge from to? Yeah, I can. Yeah, this is how I've done it anyway. So yeah, so I can just say this dot add directed edge from to, and oops, I really hate this. It's horrible. I have to see how I change this. So as soon as I press this button, I have to press it twice to get the quotation marks. Anyway, so this dot add directed edge to from, and this way I'm reusing both methods that I've already written. Okay, and that's that for now. Let's do the other one. So contains. Okay, return this dot vertex set dot find by value. I want to give the value here, different from null. Okay, so this this find by value, if you remember the way we implemented it, it's either gonna give me the value. Let's see, how was that done? Find by value. Where was it? Was it in the vertex list? All right. So if we can find one, meaning that if it's different from no, we're gonna get true. If we actually get no, we're gonna get false, meaning that we haven't found it. So yeah, this is a conditional statement, and I would rather put it in brackets so that it's more clear. Okay, after that we have the same for the vertex. So return this dot vertex set dot contains vertex, which is what I've just done up here. All right, remove. Let's see how to do that. So if vertex to remove is null, then what I want to do is return false, the first thing. After that, okay, so if it's not null, then I want to say this dot vertex set dot remove, and I want to say vertex to remove. Okay, and can you think of as soon as I remove a vertex, I have to do one more operation to keep my logic as is. Yeah. Delete all edges connected to it. All right. So let's see. For each vertex T vertex G vertex in this dot vertex set int index equals G vertex dot neighbors dot index of vertex to remove. Okay, so the first thing that I want to do is I want to find if I have the vertex to remove. I want to find it, and if I can find it, meaning that if this index is a positive number, then I would like to remove all of the occurrences of this vertex to remove. So exactly, if index is not -1, means that I have found a match. I want to say G vertex dot neighbors dot remove at index. All right, and I would like to remove the weights as well. So weights dot remove at index. Okay, and one thing remains. I want to say true. Return true. All right, so if we have a null, so if someone here has giving us something that is null, then we want to return false. Otherwise, remove the vertex and do checking whether it's in some of the neighbors of the other vertices. All right, this one is gonna be very similar and a lot quicker, I assume. So I have to say vertex T vertex to remove equals this dot vertex set dot find by value, and I want to say value here, and then I just want to reuse the code from above. So return this dot remove vertex to remove, just reusing the one above. I'll leave those two for the end because they're a bit weird. Let's go into the properties. So I have count, and I just want to be able to get it right. I should not be allowed to set it. So I want to say get, and inside here I would like to say return this dot vertex set dot count, right? If I want to check the count of the graph, this is gonna mean get the count of the vertex set. Okay, what else do we have? We have the vertices. So again, I don't want to be able to change them, so just to get, and I want to say return this dot vertex set, which is fine, and the indexer finally. I just want to be able to get that as well, and I will say return this dot. Can you tell me what I should return here if I want to access the? So this means this is an indexer, and okay, so if I have I would like to be returning a vertex. So this is that thing here, and I already have the index. So what do you reckon I should return? The index of vertex set. Vertex set of I. Do you know why I can use this? Of index, yeah. Do you know why I can use this? Why I can say, okay, so this is the first time that I've implemented an indexer. I have not done it before. Vertex set is of type vertex list, and it has an indexer even though I haven't implemented it. Can you guess from where am I allowed? From the inherited collection. So if I go back here, vertex list collection, pressing F12, I have the indexer here, and this is what allows me to use it inside my graph. Okay, let's go back to the get enumerator and the second one. So to be honest, you have to very rarely know how to use this, and I couldn't find someone in the company that has had the need to do this recently. So I just looked it up online, and it was fine. So here, what you have to do is tell the method return all of the values of my vertex set one by one. That's all that is. And to do that, I just have to iterate through them. So I have to say for I to this dot vertex set dot count, and after that I just want to say let me just find it. This dot vertex set. Now I don't need to do this. I already have the count, so I'll just say this. This dot count, and after that, what do I want to do? If I say return this dot vertex set of I, what's gonna happen? You think? It's not gonna go through the for, so we're just gonna execute once and then just leave the for loop and leave the method in general. So to get rid of that, you have to say yield return this dot vertex set, which means that it's gonna return them and then another one and then another one and then another one until we get through all of them. And this is what the for each does. If you think about it, it just lists, it just gives you all of the values in here that you normally cannot change. Okay, so once we've done this, I just need to copy it up here so that I can implement the IEnumerable interface, which is just going to be return get enumerator. Should I put this here? Yeah, okay, and that's that. So now our graph is ready. Nothing so... Was there anything too complicated here? No, it's quite abstract, I think, but in any case, I think it would be fine. Yeah.
Can we have vertex with two vertices with the same value?
Can we have two vertices of the same value? I think you were a bit late, but we've already done that. So let me get back to it again. So here, add a vertex. The first thing that I do is I go through every single vertex in the vertex set. Then I check if one of them is the same as the one that I want to add. Then I want to throw the exception which tells me that I cannot add vertices of the same value. So if I have not done this, only then add the vertex to the vertex set. So yeah, they have to have a different value, otherwise how am I gonna access them and find differentiate between them if I have a couple of vertices which have the same value. Alright, so let's play around, let's play a bit with what we've just created, and you see how easy that is. So now if you didn't get this, all of it, just think that okay, so now we've done it and we can just use it, and let's see how easy it is to use. So graph, and I'm not allowed to use it because I don't have the using, so I want to say using generic graph dot model. Okay, and I want to say now graph of int my graph equals new graph of int. Okay, and what graph should we make? Actually, I don't have a picture, so can I run MS Paint? No. All right, just give me a second. All right, so let's make a simple graph. So let's do a vertex here, maybe 2 of these, 1 here, 2 here, and maybe I don't know 3 here. Okay, how does that look? You know, just to check. All right, so this will have label 0. This color is not good. 0, 1, 2, then we have 3, 4, 5, 6, and 7. Okay, I want to create the graph, and then I want to maybe list all of the vertices of all of the neighbors of each vertex, and let's see if we can do that. So I'll leave that somewhere on the side there. No, it's fine. All right, so now we can see both. All right, so let's do that. So I want to say my graph, actually let's do it in a for loop. So how many edges do I have? From 0 to 7, so to 8. Okay, and I want to say my graph dot add vertex. Okay, so now see, this is everything that we have here. Let me zoom in. So directed edge, undirected vertex, contains count, and that's pretty much it. A couple of more at the bottom. Remove and then access the vertices. So you know, it's pretty simple what we've just done, and it should be relatively easy to use. So my graph dot add vertex, and I'm going to say I to add all of them. Okay, and after that, what do we want to do? I want to say my graph dot add undirected edge. Okay, so I have one from 0 to 1. I'm going to copy this how many times? 2, 3, 4, 7. 6, 7. Okay, I have one from 0 to 1. I have one from 0 to 2. I like to separate them this way. Then I have another from 1 to 3, from 1 to 4. Then I have from 4 to 5, 4 to 6, and 4 to 7. Okay, is that clear? All right. And now what I want to do is, for each vertex in my graph dot vertices, I want to print, so console write, I want to say you see vertex. So if I just leave it like this, I'm not gonna get anything, right? I'm gonna get some description of the class, and I want to say vertex dot value. And now if you see here, I have the neighbors. Come on, neighbors, value, and weight, and the rest are coming just from the object class. Okay, so I want to say vertex dot value. So I want to print the value of my starting vertex and then see all of the neighbors. So to do that, for each var neighbor in vertex dot neighbors, and I want to say this space first. Yeah, let's do space first. 0, and I want to say neighbor dot value. Okay, and to make it look better, let's put a new line here as well. All right, let's have a look. I don't imagine this is going to work from the first time. Yeah, this should be just line without the line. All right, let's see what we've done, whether it's actually correct. All right, so 0 goes to 1, and so this is 2 here. 0, 1, and 2 are the neighbors. 1 has 0, 3, and 4, which is correct. 2 has only 0, which is correct. 3 has 1 as a neighbor. 4 has 1, 5, 6, 7. 5 has 4, 6 has 4, and 7 has 4. So it works. Yeah, question. What if you have a vertex which has no neighbors? Is the question. Well, let's make one. Let's say here up to 9. So I'll have a vertex which is somewhere around here and is with the value 8. Okay, let's do that. So I've added it. I don't have any edges to it, and 8 has nothing. Yeah, because it's vertex set is empty. All right. Any questions here? Everything fine? Nope. All right. So this is not very helpful now, right? So let me just close this down. Maybe we can use it a little bit later. What happened? All right. So, but this is not very interesting, right? We just list information, and what I would actually like to do is something interesting, and the first thing will be implement the depth first search. So let's get back to the presentation. I have a slide for that. So generic class quality code, I really try to keep it as good as possible. Maybe there are some things that I didn't do well, maybe some empty lines, as we know style code really likes that. Okay, then we have inheritance. We sold that with the collection, okay, and the interface, sorry, the more abstract class collection gave me everything that I needed for my vertex set, so I didn't have to write that much code. I have many things already given. All right, then we have abstraction. So we used some interfaces, we implemented them. Encapsulation, so some of the fields were private. I told you how normally the vertex and the vertex set should be internal, because we never use them, right? We only use them through the graph, and the graph is allowed to use them. But right now I can just create my own vertex, which maybe is something that I don't want to do, or I want to be able to create my own vertex list, which is something that I don't want to be able to do. It just depends on your architecture. So cohesion, this was, can you remember what that was? It was from the lecture from two days ago. Cohesion is when every method and every class does only what it's supposed to do, and not something else. It's not like a magic method. So I don't have class graph which has the graph, the vertex, and the vertex set, maybe the algorithms inside that we are gonna write. So everything is like a separate piece of code. Coupling, I don't have anywhere coupling with the console or anything like that. The only coupling that I have is with the graph, which has a vertex set, which is a list of vertices, and that's that. Okay, it's just a property, and then I work with it. But you know, they should be coupled, because how am I supposed to do the graph otherwise, right? It has to have vertices. Okay, algorithms, we haven't done any, but we'll do some now. All right, depth first search is the first algorithm that we'll do. It's relatively short, as you can see. And right, so what we are gonna do, we would like to find every single value in my graph. Actually, we can implement this one to test our algorithm after that. So what we do is we start with a vertex, okay, and after that, we go through the neighbors. So we have B and C. Let me actually draw here. This has to be drawn. So we have two neighbors, which are B and C. Okay, I am gonna choose the first one, B. Okay, after that, I have two more for B, which are D and E. I choose the first one, D. So it's like this, and then here. All right, now D has only one neighbor, so I dig deeper. This is why you know it's depth first, because we go first through the depth through the neighbors of each vertex. Okay, then I found H. Okay, H doesn't have any neighbors, so I print H. After that, I go back to D. I see that D doesn't have any neighbors, so I go back. D doesn't have any more that I haven't visited. Then I go back to B. I print D in the meantime. Okay, now we have B. B has another neighbor, which is E, which we haven't visited. We go through E. E has two neighbors, which are I and J. I go through I. I doesn't have any neighbors, so I go back here and I print I. Okay, then we go through the next neighbor, which is J. J doesn't have any neighbors, so I have to go back. I print J. We go back to E. E doesn't have any more that we haven't visited, so I print it. I go back to B. We visited everything with B, and then we go and then we print it, and we go back to A. Okay, once we are at A, we just check the other side, which I am not gonna do. Is that sort of clear? We look through the deepest possible neighbor. Sorry, for each neighbor, I would like to check the neighbors of it, and then the neighbors of it, and as soon as I don't have any, only then I can go back and print whatever I have. So just to finish this, so I have HDI Normally the vertex that you start from is given first, I think, or I don't know, we'll see once we implement it. So I will go to C, then to F, then to K. Then I want to go back to F, so I print K. Then I want to go back to C, I print F. And then the last one is G. Then I print G as I go back, and then I print C as I go back, and then I'm back to A. I have no more neighbors, so either I print it first or I print it last, however your algorithm is implemented. Is that clear? Depth first search, and now I've listed all of the vertices that I have. All right, breadth first is a little bit easier, I think. So first you go through the children of A. So this is B and C, so I type them down, B and C, maybe A first as well. Then I go through all of the second level children, which are D, E, F, G. Then I go through the next level, which is H, I, J, K. Okay, this one is simpler, I think, to implement, so this is why we are gonna do this one. So if you remember, I mentioned that so for each vertex we look at its children, and in this case B. I look at the neighbors of B, which are D and E, and then I look through the neighbors of D, which are H. And if I have more, I have to just go through the neighbors of each time, which is what recursion is about. So I cannot do this with a for loop, right? Because I don't know how many children down the line am I gonna have. So in this case, I can have 1, 2, 3. I think 3 for loops are gonna do the job for this specific example. But if I have more children here and more, I would like my algorithm to be able to work for every single one of them. And this is why we're going to use recursion. And I'm not gonna get into too much detail about it because it's not that easy, but I guess from the code it should be relatively simple to guess what it does. Alright, so let's add another folder, which is gonna be algorithms. And I actually have to pull. Alright, so let's get back here. I want to add a class which is going to be called DFS, depth first search. Alright, so the first thing to do is delete all of that. I would like to use generic graph dot model. Because we are going to be working on a graph. So since this is an algorithm, I don't want to create instances of it. I just want to be able to use it. So this has to be a static. Okay, so static class DFS, and since our public static class DFS, okay, and since we are going to be using graphs of T, this has to be of T as well. Alright, so the first thing, private static vertex list of T. This is going to be DFS list. This is going to be what we are going to present as an information to the end user. Alright, okay, so let's do that. So public static vertex list of T compute. Okay, so this compute method is gonna return the answer, which is gonna be in the form of a vertex list. So imagine that thing that I wrote, like B, F, G, I, and so on. This is what we are gonna get in the end. So this is what I'll return in the end. All right. So what do we need? I need to have a graph of T, graph. So this is going to be the graph that will be traversing, and then I want to have vertex T starting vertex. Okay, clearly I need those two things. Okay, here I would normally check whether the vertex is inside the graph or not, but you know, we're not going to bother with this right now. So first, every time when I want to compute, I would like to clear my list, so it's going to be DFS list equals new vertex list of T. Alright, DFS list dot add starting vertex. So the way I want to implement this is I want to add it to my list at the beginning so that I don't have to worry about it in the end in the recursion. In the method which is going to be DFS. Okay, so now here I want to say depth first search of starting vertex, which is going to start my search. Okay, and once I finish with this, I would like to say return DFS list this way. Alright, the only thing that remains is to implement this method, which is below here. Alright, so private static, it actually, I don't want it to be void, I want it to be vertex of T. Alright, okay, so how do we do that? So I said once we start the depth first search, I would like to search through every single of the neighbors of this one. So this is what we'll do for each neighbor in vertex. So it doesn't always have to be a starting one, right? It can be somewhere in the middle, so I'll just give it a more general name. So for every neighbor in the current vertex, maybe current is better, current vertex. Okay, so for every neighbor in here, neighbors, of course, what do I want to do? Okay, so first of all, I want to check if I already have the neighbor in my list. So let me go back to the picture in the presentation. So let's see that let's say that we are here, then we went here. Actually, no, this one is not good. Let me do that again. So if I am here, then I am here, then I'm here. Okay, so now as I'm going back to E, okay, I already have I in my list, right? Because I am going back. Once I'm at E, I would like to be able to choose the other vertex and not go back to the original one. So I want to check if I already have it in my list, and only if I don't, I want to go to this neighbor. Is it, yeah? Question?
Go back to B if it's undirected edge.
Go back to B if it's undirected. Well, no, these arrows here, they are just undirected here.
Yeah, so if we are on E,
If we are on E,
B isn't in the list yet.
yeah, B isn't in the list yet, but I want to be able to go back through this route, but I don't want to be able to go through to I again, because I've already visited, right? Okay, you'll see in a second, and I hope that it will become clear. So if DFS list dot contains neighbor, so I would like to go deeper only if it's not in my list, and if it's not, I want to say DFS list dot add neighbor, and after that I want to do the same method, depth first search of neighbor. Alright, so I add it, and then I do the same for the neighbor. So I am gonna go back here. The neighbor is gonna become my current vertex, and now look through every single neighbor of my current vertex this time. If you don't understand this, I really don't want to go into depth. We'll have a separate lecture sometime in the future about recursion, but I hope that this is clear enough. So the idea here is that I want to check for each take a vertex for each of its neighbors here, look through the neighbors of that, and so on. I want to do it as many times as possible, and this is how we do it with calling back the same method here. Okay, and finally I would like to say down here return vertex, so that I'm allowed current vertex, I wanted to say current vertex, so that I'm allowed to put it in my list as soon as I do it. All right, is it clear, this one? Even if it's not, let's just check it with the graph that we currently have. If you don't understand it now, it's fine. Just remember, this is the DFS, and it's just a couple of lines of code. It's not that complicated. Right, so let's get back to the entry point. And am I here? Okay, I am here. So instead of listing all of them, I would like to just call the DFS on the graph that I've already created, but I want to change this to an 8 so that we don't have an empty vertex. All right, so our graph is here, and we should expect like 0, then 3, 5, 6, 7, 4, 1, and then 2, I guess. We'll see. But in any case, the idea of the algorithm is to find every single value that we have, so that we've searched through all of them. All right, so what do we do? Var result, because in the DFS here, what I have is, let me find it. This is what we return, a vertex list T. So I can just say here vertex list of int result equals, and I want to be able to access the algorithm, so I want to say using system dot no generic graph dot algorithms. Alright, vertex list result equals DFS of int, and inside here I would like to call the graph, which is my graph, and I also want to call the vertex, which is going to be 0. Cannot be used like a method. DFS.compute of int. I'm not allowed to do that. Have I done a fix for this? No, I haven't. So let's do this. My graph of 0. Right, so the problem was that I don't have the compute method, which is going to take just the value. I can do that, it's going to be just a couple of lines, but instead we can just say my graph of 0, which is now going to be of type vertex of t. Alright, so now that we have that, I would like to be able to get what's in here. So let's print it. For each vertex in result, I would like to say vertex dot value, and let's hope this works. Alright, so let's have a look. It seems to work. It's not exactly what I explained, but let's have a look. So we have 0, we have 1, we have 3. Okay, we have then 4, 5, 6, 7, and then the last one is 2, which seems to work. It's not exactly what we want, and 1 second. It's not exactly what we want. Let me check if I can fix this now. If I just give me a second to think about that. Alright, so we did a slight modification to the algorithm. So I added a helper list, which is gonna see which members have I passed through and which ones I haven't. And I'll be using it the same way as I was using the DFS list here. With the one key difference that I would actually like to add the vertices to my DFS list as soon as I start getting back through the end route. So I want to add the 3 first. So I want to go 0, then 1, then 3, and as soon as I start going back, which is this return here, only then I want to get this one vertex, and now it works. So if we just do that, if we print that, it works, and we start with 3. So the first one is 3, then we have 5, 6, 7, then we have the 4, the 1, then 2, and then 0. And now this is in the correct order. Alright, okay, so this was still not that interesting. And the really cool thing now would be the next thing, and what we are going to do is we're going to hack the Wordz game. So yeah, okay, let's do that. To do that, let me first explain what Wordz is. So let's go back here. So we have a table with some letters, and what we want to do is to find every single word that we can get from it. So I'm allowed to go right, down, diagonally as well. I'm allowed to use any direction that I want, and I can start from any letter that I want. So if I want to do this path, it's fine. If I want to do something else, like go around and so on, this is fine as well. The only thing that I'm not allowed to do is revisit a vertex, in this case a letter. So I'm not allowed to do something like this. Okay, and the idea is to find as many words as possible. And this game is actually quite popular. It's called Wordz. In Bulgarian it's called O Dumi. Dumi means words. And yeah, so it's quite popular, and actually recently there was Wordz 2, which is new and has some new features and so on, but we'll hack both, so it doesn't matter. So to hack this game, what we actually want to do is we want to have a dictionary of all of the words. Let me actually type, this is better. So we want to have a dictionary which is going to contain all of the words in the Bulgarian language, or as many as possible depending on what we find. We're not going to do that ourselves, and more importantly we would like to be able to generate every single path that we can get from this table, right? Every single path. And this is not DFS, because DFS only is only gonna list all of the letters here, right? It's not gonna give us all paths, and actually what we want to do is get all paths. So why are we using graphs and not just do a table and search for all of the paths there? Well, a couple of reasons. The first one is that graphs are normally faster, because inside here, every time I have to check when I am choosing a direction, I have to check whether I am going outside of the array, right? And with the graph, I only have connections. So the only thing that I'll say is Z is connected to G, so this is G, is connected to A, and then it's connected to another A. So anywhere here, so I am not checking anywhere whether I can go outside of the array, or outside. I only have three checks here, instead of having to do for each tile I would have to do 6. And by using graphs, I am saving probably around a half of the checks, maybe a little bit less, but I'm saving about 30% of the checks, which is is quite huge, especially if you want to find all paths, which I've calculated to be around 12 million. So imagine for 12 million paths to on each step having to check whether you go outside of the array, and this is going to be actually a lot faster. Right, so this is what we are going to do. The idea is to create a graph. So first we would like to create the algorithm which finds all paths. After that we are going to get the dictionary. We are going to get all the paths in a file, so that we don't have to calculate them every time, because it takes around 30 seconds or so, I think. So once we find them once, we're going to save that in a file and then load it from there. Okay, once we've done that, I just want to check, well, is any of the this is paths. Okay, I want to check if any of the words in my paths here match any of the words in the dictionary, and that's that. And if you think that's quite a lot of paths and quite a lot of checks, and normally it would be quite slow, but I'm sure that we'll be able to optimize it enough so that it works. And the idea is, in the end, for the program to just print all of the words that we have inside the dictionary. Inside this thing. In order to do this, I wanna create a graph where each vertex is gonna have the character, and the neighbors will be the neighboring characters. So as I said, A, and then I have a G. we don't need what? We can do it diagonally. So the question is in the game whether we can do it. Yes, we can. We can go diagonally as well. Unfortunately, if we couldn't, that would save us, a lot of checks. But actually, we can. All right. So let's get back into the code. Let me pull. Right. So what remains to be done is the coolest part of the lecture, which is we're gonna hack this. To do that, first we're gonna implement the algorithm which is needed to give all paths. So let's do that. So let me add a new class, which is gonna be called get all paths. Maybe is a good name. All right, let's delete all of that. Delete that. Make it public. So public static. Then of course we are gonna need some usings. So using graph theory generic graph. Is that it? Dot model. Right, and what else? I am gonna be using system dot collections dot generic. And using system.link. So link is that cool thing that I explained in one of the previous lectures, and we show how you can use it, to save you a lot of work most of the times. All right, so let's think about how are we gonna implement this first. So now we have depth first search, which you know what it does, right? So let me do that very quickly again, and please try to think, if I want to get every single path in my graph starting from 0, while I do the DFS, think about at which step I should be adding the vertices to my path. So we start from 0, we go to 1, then we go to 3, then I want to go back, and I want to go to 4, I want to go to 5, then I want to go back to 4, to 6, go back to 4, 7, and so on. Okay, and let's get back. So get back to 4, get back to 1, and get back to 0. Okay, so so far I've went through all of the paths that you can think, but it was sort of hidden. So right now the only thing that I'll have as a result is 3, 5, 6, 7. What's 4, 1, 2, and so on. I've done it up to here. So yeah, I only get this, right? But this doesn't give me all paths. And I've actually gone through all paths. So can you tell me at which step I should be adding either the vertices or the current path or whatever you think? No idea whatsoever. Okay, so I've just explained that we go. So imagine this now. I get into the DFS. I get back to the previous DFS and so on. But I only print some specific values which do not give me all of the paths, even though I have went through them, right? And I wanted to ask at which step. So right now the step in the DFS is just when we go back, right? Only when we go back, only then I add my vertex, right? But it doesn't generate all paths. So at which step do you think through all of this path that I've just described, where do you think I should be adding the vertex to get,
But what are we doing? Are we searching for one?
We want to search every single path in the graph starting with 0. So if I want to find all paths in my graph, I just have to find all paths starting from each vertex and then iterate through all of the vertices to find all possible paths, right? You probably so yeah, on Saturday I said that this is how we are going to do it. So we are going to create this graph, which is gonna say which letter is connected to which letter, and I just want to go through all paths in this table or in my graph. And yeah, so we are gonna model this with a graph, and I want to find every single path in the graph. And to do that, first I have to find every single path with a starting vertex. This is what I want to do. So idea back there.
Every time we enter the method, we have the current path to there, and every time we enter them.
All right, so every time when I enter, so the first thing to do is to add the 0, right? So add 0, right? Because this is my starting. I want to know where I start from. So this is going to be done in the very beginning. Okay, after that, every time when I enter a neighbor, I'm going to put it here as well, right? This is going to be 0, 1. Then once I get to the 3, I am going to write that in as well. And now comes the hard part. So I have 0, 1, 3, which is a path. What happens if I want to go back?
You return the whole thing
Okay, so I save this and remove the last one. And this is what we will do. So every time when I want to go back, the first thing that I'll do is to save this path somewhere somehow, and I will remove the last one so that the next path will be 0, 1, 4, 5. I'll get through here and here. Now I have this path, right? And I wanna go back from the 5. As soon as I wanna do that, I wanna save this, remove the 5, and so on. And this is gonna give us all paths. So let's do that. It's very similar to the depth first search, but with some additions, I would say. All right, so let's get here, and let's see what we are gonna need. So private static list list of vertex list of t, and this is gonna be called I have to say here get all paths of t, of course, and this is gonna be all paths with a starting vertex. Okay, this is a good name, although a bit longer than I wanted, but this really explains what it is. So I am gonna keep all of the paths that I listed here. So what was that? 0, 1, 3, and then we had 0, 1, 4, 5. And every time that I want to save this path, I want to save it in a list, right? And this is a collection of vertices, right? And so this is why I need a list of vertex lists. So vertex list will be every single path, will be a path, and I want all of them, so I'll just store them in a list. Okay, let's do the other one. So private static vertex list of t. This will be iterator list. Okay, so this will be the list that we use to add and remove vertices and so on. This will be the thing that we use throughout the algorithm to save all of our paths. Is that clear? The one where you said that we delete and we add and so on. So this will be what we'll use. And since we want all paths, okay, it will be very easy to do in the entry point here, just to say, well, do this algorithm for every single vertex, but we'll do it a little bit simpler for the user to just say, well, I have a method that will calculate every single path with a starting vertex, and after that I'll have a method which is just going to calculate all possible paths independently of the vertex we choose as a starting one, so all paths. So this is what we have. So private static, and I'll use dictionary, and I'll explain why in a second. Vertex of t, and after that list of vertex list of t, and this will be all paths. Okay, if you got the one above, right, this is all paths with a starting vertex, and it's of type list of vertex list of t, which is this thing here. The key in my dictionary, so every dictionary has a key and a value. The key is unique, and I'll just store here. I'll just store my starting vertex as just as an address for my paths. So imagine that here I'll have a dictionary, like a normal one. Here I'll say 0, and as a value I'll have all paths. Let me type this. Can I? Yeah, make it smaller. So this will be all paths with starting 0. Okay. I'll have a 1, and this will be all paths starting with a 1, and so on. And this is my dictionary, right? And I won't have here repeated keys, because I'll just go through each vertex precisely once. Is that clear? Just how do we store the information? It's a bit hard to access it afterwards, but I'll show you how to do that. You just have to go through the dictionary, go for every vertex, look through the values and so on, but we'll see how to do that. It's not that complicated. Alright, let's have our method compute. So this will be the main one, or the one which calculates this. Once we have all paths with a starting vertex, then it'll be very easy to fill in this one as well, the all paths, and we'll do that in the end. Okay, so here I have public static list of vertex list of t, and it's going to be called compute. And what do you think we need inside as parameters? Okay, vertex. So I'm gonna say that vertex of t, starting vertex, ups vertex. And what else do we need? We need a graph, right? We need a graph, a starting vertex, and after that everything will be fine. Okay, so let's do that. So graph of t, and we'll call this just graph, the one that we'll use. Alright, and the return I'll do a little bit later. For now, let's just do return all paths with a starting vertex, like so. Okay, after that I wanna do something with it, but you'll see. So so inside here, can I select this? So inside this method now, I wanna fill in all paths with a starting vertex, and after that I just wanna return it so that someone can use it. All right. So what do we need? Iterator list equals new vertex list of t. What else do I need? All paths with the starting vertex equals a new vertex list of t. So every time when I enter this method, or every time when I want to do a calculation, this was a list of vertex lists. So every time when I want to do a calculation on a graph, I would like these two values to reset and start anew and start fresh and so on. You have a question? Yes.
I didn't understand, what are we going to use the iterator list for?
Okay, so the iterator list we are going to use to store the current path that we have. So let's get back to this example. Okay, I start with 0. So this now is my iterator list. Okay. I shouldn't have done that. Let me remove that. Can you be bigger, please? Whatever. Alright, so yeah, we start with 0, so this is the iterator list again. Okay, we start with 0, we then add 1, we then add 3, yeah? We save, okay, and still in my iterator list, I'll remove this 3, and continue, 0, 1, 4, 5, save. This is the iterator list that just keeps all of the information. Right. Okay. Right, so in the iterator list, we said that we have to add the first element because we always start with the 0. So iterator list dot add, and I want to add starting vertex. All right, and I want to do depth first search. So we do pretty much the same algorithm with only a couple of differences. We described that the only big one will be where we actually add and copy the current path or the iterator list of my vertices. So let's call that depth first search. Depth first search. No, I'll write a new one. I'll write a new one because it's modified, right? It's not exactly the same. Okay, so here I would like to just give starting vertex. Yeah, and let's now implement it. So inside here I would like to get vertex of t. How did I call this? Current vertex maybe, or just vertex? All right. Sorry. Right. So we would like to initialize first. I'm sorry. No, this is something else. Just give me a second. Right. So let's get on with it. So I'm in a vertex, and I want to just look through all of its neighbors. So for each, and I want to say var neighbor in vertex dot neighbors. And just one second. Right. Okay. So for each, I would like to do the same check that we did before. So I don't want it to contain. I don't want it to go back the same path that I started with. So once I enter the 1, I don't want to go back straight to the 0. So I want to make the same check as before, which is going to be if iterator list dot contains, and inside here I want to say vertex. So I do not want, so if one of the neighbors goes back to the same one. Is this correct? No, it's not. This should be neighbor. All right. So this is exactly the check that I said. So we do not want our list, which we already have, to contain the previous number that we had. So in this case, I've already added the 0 here, the starting one. So once I enter the so our iterator list has 0 here. Once I entered the 1, I'm gonna check. Well, if the current neighbor is 0, then I don't want to deal with it, and I've already stored it in my iterator list, so I can only check there. Right. Okay, and after that, it's we have to add the neighbor. So we said every time when we enter a neighbor, when we go further into the search, I want to add the neighbor, iterator list dot add, and I want to add the neighbor. So this thing says as soon as I'm at the 0, I go to 1, and as soon as I'm at the 1, I have skipped the 0, so I cannot go back. Okay, so we know that that's true with the if check. So once I found a neighbor which doesn't do that, which is now 3, I want to add it straight away. So I'll have 0 as the first one, I'll have a 1, and as soon as I can enter further in, I can just add the 3 as well. Okay, is that clear? This is what this line does. Okay, and after that, I just want to do the depth first search of neighbor as well, to go further in if I can. Neighbor. All right, and now the the interesting path, sorry, the interesting thing here is what we do in the end. So inside, outside of the for each, if I don't have any neighbors, I've reached the end. I wanna return, or I wanna go back to the path, or stop the recursion. And this is the more interesting thing. So what we do, so now I have found the path, I have to go back. So I have found 0, 1, and 3. There are no more neighbors, so I'll reach this return, and I'm gonna go back a step to the 1. So what do we do at this point? Okay, I want to save it, and I want to remove the last one. All right, so let's do that. So all paths with a starting. Oh, come on. All paths with a starting vertex dot add. And what do I want to add? Iterator list. And okay, so can anyone see a problem here? So let me just write the next line, and we'll discuss this. So iterator list dot remove at, and I want to remove at iterator list dot count -1, just to remove the last one. So once I've added, so I have the again 0, 1, and 3. I should better just write it out, because it's there all the time. 0, 1, and 3. All right, so now that I've saved it, so saved, I want to just remove the last one. And so this is the save is this line, and the removing is this line here. So I just remove the one that's at the last position, and then I want to go back after that. So after these two steps, and when I say return, the iterator list will be 0 and 1. Okay, and then we can go on to 4, and then 5, and so on. All right, so a problem here. We need to clone it. Why?
Because it's a reference type, so when you change it down the
So if it's it's a reference type. So when I change it, in the end, I'll have a list here of vertex list, which will be the same for for every path that I want to have. So here I have to say .clone to make me a new list, and then save it, so that I don't get copies of the same thing. Because if I don't have the clone, I'll just have a copy of the reference, and I'll have a list which only has copies of the same list in the end. So I really want to get into this clone. So if I press F12, this is going to take me to my vertex list class, which we have, and this is the method clone that we had to implement. If we didn't have this, the collection, I don't think, has a clone method. No, it doesn't. So we had to do it ourselves in order for the algorithm to work, right? There is no other way for us to just copy it straight away. And this is what the clone does, and we actually create a new list which points to a new address in the memory, and we just copy every single value, and then we bring back the new list. So this is how it's done. Right, so let's get back here. I think this is pretty much done, to be honest. What do you think?
But wait, if we remove it from the iterator list when we go back to the previous depth, won't it go back to the 3 because it's already removed?
So the question is, once we get to the 3 and we want to go back,
We remove it from
we remove the 3. Yeah.
and it checks if it contains.
Yes, but
It checks if the
yes. So yeah, I get it. So the question is, if I go back to the 3 here, and I type it, I saved. Damn it. Second. So yeah, we have the 0, 1, and 3, and I've saved it. I've removed the 3, and then at the next step I have 0 and 1. So in this check here, I am not gonna have the element 3 inside, right?
Yes.
And the question is, am I not gonna go back to the same 3 and just make an infinite loop? Well, the answer is no, because I've already visited the neighbor and it's gonna visit them one by one. So once I start going out of my path, so 0, 1 and then 3, and I did the same thing again, so 0, 1 and then 3. So once I go back and remove it from the list, in this for each, I have already went through 0 and 3, right? So they're not a concern, and I'll just continue from where I stopped. So 0 is not fine because I am going back. 3, I have already went there, so I am going back, and I'll just continue through my path.
Okay.
Yeah, is that fine? Okay, this was a good question. Right, and the last thing that remains to be done is if I have a graph here, and I don't want to specify the starting vertex, but just find all possible paths, then let's do a method for that as well. So it will be private static, and now I have to return this, which I really don't want to write by myself, and this will be again method compute, and here I only want to take a graph. What is wrong with you? So compute graph of t and then graph. Okay, and the algorithm is pretty much the same, so nothing that special there. So here I wanna reset the all paths dictionary. So every time when I wanna use it, I just wanna reset it. So I'll say new, and thank God for auto complete, because writing this is a nightmare. But yeah, anyway, so here. Okay, and then we just want to apply the algorithm for every single vertex. So for each vertex in graph dot vertices, please. Yeah, I just want to apply the algorithm. So how do I do that? All paths dot add, and inside here I just want to say vertex compute graph vertex. Okay, I'll explain this line in a second, and in the end I just want to return all paths. Alright, so as we said, this is a dictionary which holds the vertex that we started from, yeah, and then it holds all of the possible paths for this specific vertex. So in my dictionary I want to add the vertex that I start from. Actually I can rename this current vertex sounds better. So add the current vertex that we are checking all paths for, and then after that just compute, and this is my graph and this is my current vertex that I want to compute for. So I'll just be reusing this method above, compute. To keep quality code, I have to take this and I have to put it in here so that I can see both of them one after the other. Okay, and this is just a helper, so this should be public because I want to use it, and the one above is just used for calculation, so it has to be private. No one has to see how I do my computations, just the result of it. Yeah, what do you say? Let's give it a go with the current graph that we have. So oh yeah, there is one more thing that I wanted to do here. So inside here I actually want to sort it because I'll get the paths in a very weird order. So let's have a look. What is the order that I'll get my paths in? So I have 0, 1 and 3. Which is going to be the next one?
0, 1, 4, 5.
The next one?
0, 1, 4, 6.
After that? For 7, then I'll have 0, 1, 4, I think. Then I'll have just 0, 1, then I'll have 0. and so on. So and then after that I will have the 0 2. So this is not a very good way of presenting our information. Sorry? Yeah, so yeah, 0 1 0 2 and then 0 in the end. So this is not a very good way of sorting. And if you had a bigger graph, say on the side of 2 I had a couple of more vertices, then here they will start getting with more numbers and so on, which is not a very good way to present the result. So to fix that, I just want to say order by, and inside I want to say x goes to, so what is x? What is x? Each path, which is a vertex list. So I want to so this x, I just want to say x goes to x.count. Okay, and this is going to sort them by the length. Okay, so now this is a problem, as you can see, and as we know, when we use lambdas we get some weird collections in there. So this is some if I just leave it like that, I will get something like I enumerable of t or vertex list of t or something like that. And actually I want to transform it to list so that it works properly. And now it works. Let's give it a go. So this is the graph that we'll look at. This is our favorite graph from last lecture, and we'll apply the algorithm on it. And once I apply it, I would like to see how many paths are they sorted, and so on. So let's do that. So we already know this, the DFS, so I'll just comment it so that you can use it later on if you want. This was just a test and I want to remove it. Okay, so I want to say var result, because it will be quite long to write the result. And here I want to say the same thing that I said above. So I want to say get all paths of int, and then I want to say dot compute. And here I want to give my graph, and I also want to give my graph of 0. Okay, first to check whether just for a single vertex if it works, and then after that we'll just remove this and it will give us all paths. Do I have results somewhere? Yeah, I have it here. So let's call this all paths result. Okay, and now printing is a bit tricky. So how should we print it? First of all, what did we have? So what is this var? We have vertex list of int. So for each path in all paths, I want to say what do I want to say? So console write. No, I need another for each, which is going to be var vertex in path dot vertices. No, for each vertex in path, I think, and I have to print vertex dot value. All right, and I don't want them to be printed on the same line. I want to say this. I want to add a space. And after I've printed every single vertex in the path, I want to print a new line as well. I could have put it at the beginning. And I'm not sure if this is going to work, but let's see. So let me put that on. Actually, I cannot zoom, so let me just put it somewhere around here. Just order those a bit more. And this thing here maybe, I don't know, here. Alright, I think this is perfect. Okay, so we have the 0, we have 0 1, we have 0 2, 0 1 3, we have 0 1 4, we have, and then 0 1 4 5, 0 1 4 6, 0 1 4 7. Yeah, works. Perfect. Right, any explanations on the algorithm and stuff like that? No? Everything is fine? Okay, I can now safely remove this. And then I am gonna get all of that and I'm gonna put it in a method. So this is gonna be testing algorithms, and I'm gonna comment on it. Okay, so now comes the cool part where we're actually gonna create the graph with the table here. We are gonna create this graph, we're gonna apply the same algorithm, and we'll see what happens. Right, so let me just remove a sheet or two. And this one, yeah, I wanted to add something else before that. So how long is the lecture now? Okay, it's fine. Inside my code, I wanted to go back to my graph to make it a little bit easier to do. I don't want to call every time in my entry point. I don't want every time to write, GFS or get all paths or something. I want to have it as an option to my graph. I want to say my graph dot get all paths as a method instead of having to look for it in the algorithms folder. So let's go back to the graph, and I have no idea where to put this, but I guess somewhere around here is fine. You think it should be? No, it will not be static because now it will be a part for the specific graph. It will be some calculation for the specific graph. So let's do that. So public vertex list of t. I'll do that for the DFS first. And inside here, what was it that we need? Vertex of t, and this was called a starting vertex. All right, and inside here, I would like to have a simple check, which is going to say if this dot vertex set dot contains starting vertex contains. Okay, so if someone has given me a vertex which is not in my graph, I would have no place to start, right? So inside here, I would like to throw the exception. So if it's not in there, if I don't have the vertex, I want to say throw new invalid operation exception, and I want to say please input a vertex, or please pass a vertex which is a part of the graph. Alright, and then after that I want to do the calculation, which will be simply to call the method which is in the algorithms namespace. So return algorithms dot gfs of t dot compute. For my graph, what do I have to say here? This, yeah, and then starting vertex. All right, and this is what we'll do for the rest as well. So I have public list of vertex list of t. This is a bit tedious now that you know what's going to happen. So get all paths, and inside here I would like to let's do first one, the one where we actually give the vertex. So vertex of t starting vertex. I want to do the same check. I think, yeah. So I have to do the same check. I'm gonna copy it now, but I must delete the semicolon. Semicolon here. Thank you. Right. So I am copy pasting, which is bad. And normally what you have to do is create your own exception, which is gonna inherit from the exception class, and you are gonna call it your own way, and you can take this check inside the method so that you don't repeat yourself. But we are not gonna get into that because it's just gonna waste time now. All right, and then I want to say return algorithms dot get all paths, and inside here I want to say this, and I want to say starting vertex, and something doesn't work. Why do you? Oh yeah, I have to say get all paths of t, I think, and now you should be fine. No? Dot compute. Yeah, this is what I'm missing. Compute. Yeah, now it's fine. I'm gonna copy this as well so that I don't rewrite it again, and inside here we'll just leave it blank because we know what the graph is, and we don't want to have a starting vertex, just compute all of them. So I'll just remove that and I'll put in here just this. I don't have a starting vertex, so I'll have to remove that as well. Sorry? And not throw the exception. What is your problem now? I should return, yes, thank you very much. So I have started already to copy paste, so I'll do that again in here. Now we are fine. Okay, now I can do the same calculation that I had in the method. So here, instead of doing this, I could have just said my graph dot get all paths, and I can say my graph of 0. Actually, we didn't check the all paths, right? We just checked the ones from 0. So let's do that. So let me first check whether this is fine and it works. I'll uncomment this. Okay, this works for the 0. We haven't broken anything, so let me do that as well. And we have a problem. Oh yeah, I'm not printing it right. Now this is a bit harder to print. Let's have a look because we are going to use it anyways after that. So we have a dictionary which has a vertex list. So var path in all path result dot values. All right, and now I have a path. Let me pause this for a second. I need to think about it. Right, since we have a list of a collection of list of paths, first we have to take every list of paths. Then we have to take every path in the list of paths. Then we have to take the vertex in the specific path, and then we can print it. I know it's a bit complicated, but you know, this is how it works. And now let's have a look, and this looks pretty. My console buffer is weird, so let me do that. Buffer height, let's put that to be, I don't know, 200 maybe a lot, 160. And now I have to restart it, and okay, there we have it. So for the 0, we already know what that is. Let's bring up the graph, which I have just closed, but I have it here, so it's not going to be a problem. So let's bring back this. Alright, so we have the 4, 1. Okay, we have the 1, we have 1, 0, we have 1, 3, 1, 4. Okay, we have 1, 0, 2, we have 1, 4, 5, 1, 4, 6, 1, 4, 7, and that's it. That's all. So yeah, it works, and we can check all of them, but like if 2 of them work, let's assume that all of them work. All right. Now let's create the table graph. So I'll just remove this. I'm gonna cheat a bit, since, you know, just adding vertices and edges and so on for half an hour, I'm sure that's not going to be that interesting. So I have this here. It's pretty much that. I'll go very quickly through this, but I'll just copy that whole thing here, and I'll explain what we are doing. It's very, very simple. I just don't want to waste that much time. Okay, and here I would like to say create table for graph. I'm not sure whether that's a good name, but anyway. So okay, so remember that I wanna make this graph. Okay, so let me put that aside so that we can probably see it. Make that smaller as well. All right, so I need to add 16 vertices, okay, and I am gonna use int instead of the characters. Do you know why? So there are many reasons, but what is like one that's gonna be yeah? Okay, I need all of the vertices to have a unique address, okay, and inside here I can have repetitive letters. But this is not going to be a problem with the algorithm that I will show how to break this game. Right, so we want to have 16 vertices, so I just add them, and then I start adding them one by one, all of the edges that I'll need. Let me just add that here. All right, so yeah, let's just check for, just pick a number between, I don't know, 0 and 15, just to check. 4. All right, so 4 is around here, so I have 0, 1, 2, 3, 4. So 4 has to be connected to 0, has to be connected to 5, then down here to 8, and this is 9. Why don't I have the 0 here? Because I've added it up here, 0 and 4. Okay, so it works. I've checked it many times, so this is fine. You have to trust me. All right, so now let's get to the more interesting part. What are we gonna do with with the graph? So okay, so I have this, get all paths. I am gonna make a new string builder, and you'll see in a second why. So the idea here is that if I put this on every time, so let me just do here datetime.now. What am I doing? Datetime.now, Control C, Control V. Okay, let's see how much time it takes for this algorithm to perform its calculations. And I have an error. The name file, all right, yeah, so I'll explain what that is in a second. All right, so let's put it on now. And this is gonna take a while. Okay, so 1 minute, but this really depends on the processing power of your PC. On the one that I use for work, it was about 30 seconds. Here it was a minute and something. So it's not a very good idea to run this every time when I want to calculate, every single path and so on. So I can do that, but the round, which is about 80 seconds up to 90, I think it's gonna just end, So instead of doing that, we would like to save it in a file, and then we can just read from it. So we've generated it once. There is no reason for us to generate it every time, because those parts are not gonna change. They are gonna be there. All right, so yeah, so this is why I create a string builder in which we are gonna save every single path. Okay, and for each value, so these are all the things that we just did, with just trying to get through the path and the vertices as well. So for every value in all paths.value, so this was list of paths, and I can rename it here, list path of paths. Okay, and for every vertex list in the list of paths, I would like to check. So this is very game specific, that you cannot get words which are less than 3 symbols or bigger than 10 symbols. So this is an optimization that we are doing, so that we are going to check all of them, but we are only going to save the ones that are between 3 and 10 symbols. Okay, so once this is true, once the count of the list is between 3 and 10, I would like to add every one of them the value, and then append a space as well. So this is because we are using numbers, so I can have a vertex with a value 10, or an address, say 11, 12, and 16. So this is why I have to add spaces between, so that I can read after that. Because if I have, say, a list of 0, 1, and then 1, 5, what does that mean? Is it 0, 1, 1, 5, or is it 0, 1, 15? This is why we add spaces. every time, and to separate or to differentiate between paths, I would like to add a new line. Is that clear? Okay, after that, as we've mentioned, when you string builder, you want to save it into a string. So all paths as string equals all paths as string builder to string. And then I want to write it in a file, which is allpaths.txt. So let's open up the folder, and let's have a look what we've created. All paths, which is 37 or 38 megabyte file. So I have tested it before with without this condition, and it was 300 and something megabytes, because the longest paths, which are with up to 16 symbols, they are there are many variations for them. So this is a big optimization. There is another way that you can optimize it, maybe save it in a binary file or something, but I just didn't want to bother with that too much. So here I really don't want to open it with Notepad because it's bad, but let's do it with this here. Okay, and here we have all the lists, and as you can see, they're pretty much sorted. Yeah, I guess they are, because they're sorted with the first with the starting vertex. If you want to see how many of them we have, this is 626,061. So yeah, quite a lot, right? So yeah, there are optimizations here. I could have labeled my graph instead of numbers. I could have labeled it with characters, and then not have all of the spaces and so on, and the new lines. I could have said, every single path is just a word, and every path is separated by a space. But this one, I found it to be nice, easy to look at, to check and so on. So we'll just leave it as is, and we'll do other what did I want to say? Other optimizations later on. Okay, I say before we get into the final part, which is actually breaking the game, I would like if we have a short break. All right, so clearly we are gonna have Right, so we are gonna need some dictionary with words to use. So let me get here and get my dictionary. You can see it very quickly. So yeah, this is it. A lot of words. I think close to 900,000. This one is already sorted, and I really want to stress on that, because the one that I had wasn't sorted the way Visual Studio wants it to be, and the reason for that is because I am gonna use binary search, and for it, that it has to be sorted. So yeah, if you wanna implement it with another language, it's very simple. You just have to find the dictionary online and do the same thing that I am gonna do now. But please remember, as soon as you save it, so I have to open it here just to show you. It's going to take you a little bit longer. So File, Save As, and here you have to say encoding to be UTF-8. Otherwise, it's not going to work with your current... sorry, it's not going to work with the console. Yeah. Okay, but I've already done that. I've sorted it, so everything is fine. This is why we have this one here, because I had to save it a second time after I've done some computations with it. Right, okay, so let's get started with this. Actually, can we get some lights on, please? Just, I would like to be able to read. Yeah, thanks. Right, okay, so let's get started. So now I don't need this, right, because I've already created the file. So let's delete all of that, and here let's just start doing. So start doing the hacking. So string characters, and inside here I would like to have some characters in Bulgarian. This did something. Please don't do that anymore. What? What the hell? Right, so change the language, input, you know, some characters here. They need to be 16, so I'll be a bit more careful. So what's that? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I guess that's fine. All right, after that, let me just change back the language. Not from here, but from here. So this is going to be just for testing. Once we finish with this, I'll just change this to console.readline. All right. So yeah, let's just put that here, just so that we know. I want to say, please input 16 characters in your specified language. All right. So what is it that we want to do? So we want to build a string builder with solutions because we are going to add, you know, solutions once we find them. So this is what we'll have. So string builder solutions SB equals new string builder. All right, and after that, I just want to read both the dictionary. I want to store it in a separate file, and in a separate variable, and also I want to read the path so that I can choose from them. So yeah, string all. This is an array. All Bulgarian words equals file dot read all lines. And inside here, I want to say Bulgarian, not here. I want to say Bulgarian Wordz1.txt, and yeah, after that, I want to store in the same type of variable. I want to say string all paths equals file dot read all lines. Inside here, all paths dot txt. Okay, nothing special. We just read over the paths and the dictionary. All right. After that, what do I want to do? I want to go through every single word. So yeah, just a second. Let me check what I'm doing here. Yeah. So if some word has a capital letter as a first one, I would like to get rid of that. So I want to go through each one. So this will be all Bulgarian words dot count, or sorry, dot length, because it's an array. And I want to say all Bulgarian words of I equals all Bulgarian words of I dot to lower. Right, because we're gonna enter, or we will expect the user to enter the characters as lower letters. Okay, after that, what we want to do? We want to say for each path, just check whether the word that the path generates matches any of the ones that I have in the dictionary. So for each path in all paths, what do I want to say? Well, first of all, I would like to have the word. I just want to be able to extract the word that I have. So var word as collection, we'll use link here, equals, and I want to say path dot split. Let's put it on a new line. Dot split. Inside here, I want to say new char. So this is something that you've done many times. So the way that I get my path as a string, as we said, was with spaces between the vertices. And here I want to say string split options dot remove empty entries. Okay. After that, what is it that I want to say? I want to select each vertex in my path. So I want to say X, or let's just call it vertex, I think. And inside here, select. I don't have a using, maybe. Yeah, I don't have a using. Now I have it. So now each vertex has to go in what? Characters of int.parse of vertex. All right, so what is it that we are doing? So remember that all paths, let me just remove that. All paths looked like, it's here, let me open it up. Let's go up. All right, so this number here will just gonna show us the position of my 4x4 table. So if we get back here, the 0, we would like to replace with this looks like a 3, but it's a Z. Then we have a G. Then we have A, and so on. So this is what I am doing here. I convert every single number in here into a character that we've added in my characters. So let's go back here. So characters is this. And I can access each of the characters, with an index. So if I have a path which starts with a 0 or is like a 0, 1, 1, 1, 2, I would like to get the this letter, and the third one, and make a word out of it. And this is what we are doing. So with this select, so each vertex or each number in my all paths, I would like to convert to characters, which was this thing here. And I want to take the vertex number. Okay. Why do I do int.parse? Because we've said and we've read it as a string, and this is why I want to say int.parse. Okay. Right. After that, I want to say the string. Sorry, vertex.length. No. It's just this number. Yeah. It's a string. I just said that. So we read all paths. This method here, file.read all lines, is gonna read as a text everything that we have in the file. And after that, I wanna convert. If I can, I can say try parse here. But let's just do it with a parse because we've created it and we know that it's only numbers that we are gonna get. So yeah, we have to convert it to a number. All right, so after that, I want to say string word equals string dot join, join with an empty space, and I want to say word as a collection, because I am not sure, as I've mentioned, I think a couple of times, when I have when I'm using link, I have no idea what the lambdas are gonna return. So in here I have enumerable of char, and I want to have it as a simple string so that I can check after that. All right. Okay. Now that I have the word, the current word from my paths, I want to check it against all words in the dictionary, or I want to find where it is. So var index equals array dot binary search, and inside here I want to say all Bulgarian words, and I want so this is the collection, and I want to search for the specific word. All right, and okay, the last thing that I have to do is just add the word if it matches to my string builder. So I want to say if index, meaning if we have found an index, just let me find it, just 1 second. If index is bigger than or equal to 0, and yeah, and all Bulgarian words of index dot length equals word dot length. So if I have something like say char as my current word, and I have character in my text in my dictionary, then this is going to be a match because it was found, right? And I want to have the specific word. So if this is word from all paths, and this is word in dictionary, if I only have the first condition, it is gonna be true, right? And in fact, I don't want to have a part of the word. I want to have the whole word. So I am checking the length of the word. So in this case, this is what, 9, and my word has length 4, so it's not a match. Okay, so if this is true, then I want to add the word to my string builder. So I have to say solutions sb.append, and inside here I want to say word plus an empty space, and this is gonna work. So this is fine. This is the algorithm that is gonna check for a match. And finally, what we need to do is just to print it. So string solutions now as string, as a string array. So sorry, not there. String solutions equals solutions. Oh my god, solutions dot toString dot split. Now I wanna split. So the way I'm adding it in the string builder is with a space, and I want to split them by that as well. So new char, here I want to have a space, string split options dot remove empty entries. This is now too long, so I'll just have to separate it as we've discussed for quality code. Okay, after I've done that, I think I have to say toArray, but let me check if I'm missing something here. No, I guess that's it. Okay, that should work. Yeah, it's fine. All right, after I've done that, I want to sort them as well. So var, because it's not going to be very nice if I just get matches which are with a different length. So I want to say var sorted solutions equals solutions dot order by, and inside here I want to say x goes to x dot length. Anything else that I want to have here to list? All right, and finally, what is it that I want to do? Just 1 second. I wanna try something. I wanna say dot distinct here and see if that's gonna fix my next couple of lines that I've written here. So I only want to take the distinct one. So if there are a couple of occurrences of each word, I just want to take that one and nothing else. All right, and now what remains for us is to print the solution. So let's do that. So for sorted solutions dot count, count, because it's a list. I want to say sort console write line sorted solutions of I. All right, and if I haven't messed anything up, this should probably work. All right, remember that I already have input some characters. Okay, exception, could not find file, generic graph. Yeah, so I have it online, but I don't have it in my project. So let's copy this and paste it in my folder. Let me run that again. Now we're just waiting. It shouldn't take that long. It really depends on your machine, because it still has to match, what was it? How many million? 1.6 million?
Does it work?
Yeah, it works. There we go. I haven't heard of that word, but I've heard of that one, of that one, of that one, and so on. So now we have it, and it works, and it's fine. Let's actually compare this to something online that I found. So I would like to say, somewhere around here, maybe. Yeah, somewhere around here. I want to say date time dot now, and I want to put it in the end as well. All right, so let's see how long is it gonna take. With my PC, with my working PC, it took about 7 seconds on average. This one is a bit slower, so I really don't know how long is it gonna take. Come on, honey. You can do this. You can match 1.6 million paths with 88,000 words, I'm sure. It was quicker last time, wasn't it?
Yeah.
Is it pressing here stopping the program? Let me just not press anything and wait for it to compute. Let's have a look. That was quite long. That was 15 seconds. So yeah, it really depends on your machine, I guess. All right, so let's compare this to something that I found online. I was gonna say that this works faster than the one online, but depending on because of this computer, it doesn't work that fast. So let's do that. So let me type that. If you have your own so I'm sure that you will be able to find something like this for your own specific language. So let me just copy what I have here. Where are you? I just want to copy this, put it online, and actually I want to count how long is it going to take. So let me put it here. So from 35. Did I press it? Alright, let me press it again. So from 45. Okay, in about 5 seconds for this specific website, I got up to 10. So it really depends on what you're testing. So ours is really, really slow, and we have to fix that. Sorry? We find more words. I like the laugh. Yeah, we actually do. But this really depends on the dictionary. So yeah. And in fact, if you know how the game works, how the Wordz game works, it only takes nouns and some verbs in a specific form, and our dictionary has it all. So yeah. All right, but I really wanna beat this website, and I don't want it to be dependent on the PC that I'm using. So yeah, so we are gonna make some improvements to this. So and to do that, I would like to use all of the cores of the processor that I have, which in this case I don't know how many are they, but when I was testing on my PC, I got it like five times quicker, or 6 times quicker, depending on the words. So yeah, let's do that. So I'm sure that not many of you have written threads and separating processes and so on, but just imagine that we can split the work into a couple of processors, processor cores or threads or whatever you want to do. So which part of this whole computation takes a lot of time, and maybe we can split it somehow. What do you think? Sorry? Comparing the list. So maybe this for each, right? Yeah. All right. So, but first, I wanna do something that is gonna help me with it. So I would like to take these here, and I wanna make them public and static, so that I can use them in a method, and I'll show you what we are gonna do after that. All right. So yeah, what else can we do? So yeah, this is a problem. I'm reading the files after we've input something. So let's say that here, instead of this specific thing, I have console.readline. Okay, and so where these were standing before, which was right here, this was not very good, right? Standing here, because I'm gonna wait for an input which is gonna take some time, and during that time I can use it, to read the files. What is your problem? Yeah, I have these stuff here. But yeah, so we can do that simultaneously. So let me take those here. Let's actually not initialize them. So let me put this thing here and this thing here, and actually create a method which is going to do all of that. So let me just copy that so that I don't lose it. Control X. All right. So now we've initialized them so that I can use them in different methods and so on. Let's create a thread. So I will do the threading thing in 2 ways, so that you can see how each one works. This is the I would say the more inconvenient way, but this is not always you can use the other method, so I'll show this one. So let me add system.threading. So thread, and I want to say read files thread equals new thread, and inside here it was taking something weird. Thread new thread start, and inside here I have to give delegate, or if you want to think, I just have to give a function to be executed. So here I'm gonna create some method which is gonna be called read files, which is where are you? Here. And here I am just gonna read the files and nothing else. So let's do that. So I want to say, how are they called? All Bulgarian words, and here I want to say all paths, and this thing here I want to delete. I want to put it up here. Control KD. Okay. Let me actually close this one up. Oh, just all paths. How did that get there? Just all paths. Yeah. Okay, it's fine now. All right. So now this is gonna be done simultaneously here. I actually have to say read files thread dot start, so that I can start it on a separate thread. All right, and okay, so what will happen if we're actually very quick here, and we've inputted the characters really quick, and this thing hasn't finished its job, right? It's gonna break the application. So there is a way to say, well, only if you finished with the current thread, then continue. So this is done with a while, and inside here I want to say read files thread dot is alive. Okay, so while we're still running the process, just do nothing and wait for it to finish, right? And as soon as it's dead, right, as soon as it's finished the work, then we can go on with our program. Okay, I think maybe I had to put this as public static, but we'll see in a second. All right, so this is fine. Actually, it's not fine. So let me put this inside as well. Here, inside here. So once I've read them, I also wanna change them to lower on a separate thread while we are printing the characters. All right. Okay, but this doesn't save us that much time, right? The reading of the file takes probably about half a second or something. The big calculation, which takes a lot of time, is this for each here. And as of Visual Studio 4.0, there is a really cool feature that you can use, and I'll show it now. But let's think about. Sorry, .NET 4.0. Yeah, my bad. Okay, so imagine if I have to, so how do we do this? First of all, I cannot do the for each. If I have to do it with threads, I have to take a for loop, I have to divide it into the number of cores that I have, and I have to do each one in a separate thread, add them to the string builder, and so on. There could be something messed up there as I'm adding the solutions. And it will be, very hard and complicated. I have to do at least 5 or 6 threads, or maybe 4, depending on how many I have. I don't even know how many I have, because there are some virtual ones. I have to check my processor and so on. So this is not a very good way to do this. Instead, what we are going to do is a thing called parallel dot. I have to input some using there. So parallel dot, and this thing does it automatically for you. So if you see here, if I zoom in, parallel, we have a for with some links or some lambda expressions, and after that we have for each. Okay, and what we are going to use is the for each. So what this is going to do is automatically get everything that's available as a resource in terms of threads and cores and so on, and it's going to do the computation for us. So let me do that now. So for each, let's see what we have to give. We have to give a source for the for each. So I have to give all paths here. And inside here I can give a lambda, I think. Yeah, I can give a lambda. So path goes to solutions sb dot append, and here I'll say calculate Wordz as a method. Okay, and we'll do that in a second. Alright, so now all of this I don't need. I don't need this as well, and I want to copy all of this calculation that I have. I want to copy it inside the method, and I'll go back and explain what. Can you see it? I can't see it. Is it at the very bottom? Where is my method? Create. Interesting. Oh no, it was calculate. Interesting. So let's do it here. Private static. I actually want to return something, and it will be of type string. Calculate word. And inside here I would like to take the current path that I have. So inside here, for every path I want to calculate word of path. And yeah, why are you not finding this? Okay, I trust you. So calculate word. So path. What kind of thing was it? It was a string. So string path. All right. I want to copy in here the whole thing. I don't have a return type. Yeah. So characters. I need to make this static as well. So public static. So let's put it here. Public static string characters, and here I'll just say characters equals console.readline. Okay, so we fixed that. Solutions.append. Okay, so I don't want to do that. I just want to store it. In some variable and then return it. So I'll just do it here. So I'll say return word plus empty space, and that's it. What is your problem? Not all call pass return. So if we haven't found anything, I want to say return empty string, so that I don't want to add anything to my string builder, because all code paths should return a value. All right. So what does this line do? Let's go back to it. So parallel dot for each pretty much spreads your for each loop into all of the cores and threads that it has. Okay, so this is the source, all paths, and then we take each path, this is a lambda, and we want for each path to append to the solutions the word if we have found it. If we have not found it, then it's fine. And I hope that this is gonna work now, otherwise I'll have to debug and do other stuff which are not that interesting for the lecture. Okay, so can we have some characters, please? Can I change the to phonetic? I actually haven't had a need, so let me just do that real quick. Alright, so we have some characters here. Let's just press enter and see what's gonna happen. On my PC it really took 2 seconds, I'm not lying. Yeah, 10 seconds. So what was the last one? It was 15. Yeah, so I guess this PC only has like 2 cores or something, but you have 4 or 8, it's gonna save you a lot more time. And I really want to stress this because this had to be on the lecture, that the first algorithm without this optimization worked for me for 7 seconds. The one online was about 10, and after the optimization with the threads, it was about 2 seconds, 1.7, 1.8. All right. So yeah, question.
Maybe we can check when we read the words from the dictionary if they are more than 10 characters.
We can check if the words that we read are more than 10 characters. This is not gonna optimize a lot of it because we are still gonna check it. What could help is to remove every single word that is that is bigger than 3 characters, which is a good optimization, but I don't think there are that many words, so it's not going to be that big of an optimization. Sorry? Yeah, we can make it just once. I just don't want to prolong the already 4-hour lecture, but yeah, it's very easy to use. So do that as an algorithm. So read it here, the words, do the calculations, which are going to be quite simple, and then save them into a new file, and then use that file. It's going to be quite easy. It will be very similar to what we've done with the long method for the graph here. So here we are doing some complicated calculations, getting all paths and so on. After that, I just store the information in a file. Another thing that could optimize this a lot is if you have a look at the words, which are not here. Not all words are in the game, so you can delete many of them. I think more than 50% of them, and I'll show you just an example here. Yeah, but it would take a lot of time. But you can do that if you want to go for really some speed. So here, out of these words which have the same root, only 2 or 3 can be actually only 2 or 3 of them can appear in the Wordz game, just because they're not only nouns. There are some verbs, adjectives, adverbs, and so on, and they don't appear in the game. All right, this was a long lecture, and we had to split it into 2 parts, and they were already long on themselves. So do you have any questions on what we've done? The real question is
was all this coding worth breaking as the game?
Breaking is the game. So there would be no point for me to actually try and break it into the lecture, into the video, but we're gonna play with it now as soon as I stop the video. So you'll be fine. We have at least half an hour of playing around with this and scoring max scores and so on. It really works. All right. Yeah. Do you have any questions? Maybe I should show once again in the end of the lecture that it really works. So I have a couple of things that I try. So these are 12, and now it's 16. No, what did I do? Let me do that again. So 6, 12, 15, 16. All right. Did this one for that specific set of letters, it took me really 1.7 seconds. Right now it took us about 8. Yeah, and we have all of the words here. They are listed. If we want to, we can reverse the order, but you know, this is not necessary now. All right, that was all. I hope you enjoyed the lecture, as it's something new and unique, and something that can be, I don't think, can be easily found on the internet. So yeah, hope you enjoyed it. I have to mention one last thing. Here is some optional homework. You know, just to extend a bit on the graph theory solution. So BFS, which is a lot easier than the DFS to implement. Read about this algorithm. It's not that hard to implement as well. Create a different type of graph, which is gonna inherit from our original graph. Read about it on the internet. You have to create a cycle and a path on n vertices, which I assure you it's going to be quite easy. Just to get into the code, into the library that we have, so that you can practice a bit more. All right, so that was it, and thanks. I hope you enjoyed it.